September 28th, 2018 as I record this preface. I'm doing this this is the solar noon video of the equinox on the 23rd, from the footage I took on the 23rd. I did a preface for the sunrise one too, and I will probably do one for the sunset one. But anyway, this is video 2 of 3, and I'm going to get through this quickly and then we'll get into the video. This video is not going to be anywhere near as long as the sunrise one, and I also will not be putting the unedited footage at the end. I want to keep this one a little shorter because the third one, sunset one's probably going to be a little longer too. But anyway, first of all, I need to explain something here. Okay, what you see here is just, this applies on the equinox only. All right, what you see here is, you see E is east, S is south, W is west, and as you can see, the sun rises in the east and sets in the west. Due east, due west are really close to it on both equinoxes. All right, so that's what this is showing you. But something else happens on the equinox as well that most people don't realize. This is going to be, this is relevant to solar noon. All right, what you see here is, you see theta. Theta equals your latitude. Theta 1 equals the complementary angle of your latitude. The complementary angle is just 90 minus theta, okay, which will give you theta 1 in this case. It's just an angle, right? Because obviously from your horizon, perpendicular is a 90-degree angle, okay? So you have to, both angles have to add up to 90. But anyway, okay. So you'll see during sunrise, theta is going to be equal to your latitude. All right. Now, yes, if the sun follows an arc in the sky, but when you're real close to it, it's essentially a straight line. All right. And for all intents and purposes, it's just straight. Okay. So it's going to be really close to your. So theta is going to be your actual latitude, and that'll happen again at sunset. Now, the theta 1 here, what you see now, relevant to solar noon here in the middle, the red arrow with the red double-ended arrow here that you see pointing towards the south, that's also going to be theta 1. Think of it this way: as you're looking perpendicular, or you're looking along your 90-degree angle here that you see in the east and west instead of perpendicular to it. That's why I just drew that line. So the sun's altitude in the sky in degrees is going to be the complementary angle of your latitude. And where I was, my latitude was approximately 41.55 degrees. So 90 minus 41.55 gives me 48.45 degrees. Okay. Now, suncalc.org for solar noon gave me an altitude of 48.20 degrees. That's a difference of 0.025 degrees. That difference I can't even measure with my Brunton. All right, my Brunton's accurate to half a degree at best. And I will measure, I set this up as close as I could to 48 degrees pointing due south to catch the sun. Just eyeballing it with bubble levels because I don't have an actual mount to do this. And as you're going to see, I was pretty close. So anyway, I guess that's long enough preface. Let's get this thing started. Hey everyone, still September 23rd, 2018. Time's about 11:50 a.m. Central Daylight Time, CDT. So that's -5 UTC. So I am going to go to the county park in Indiana, which isn't far from where I live, and I'm going to make a solar noon or culmination. Get some video like I did with the sunrise with Sarah's camera with the filter on it. I'm going to do that from there because it's the south end of the lake. I'm going to set the camera up, and what you should see across the screen is what you should see is the sun move in from left and move to right, assuming I get the angle right, which is about 48, 49 degrees, somewhere in there. I do have the Brunton. I'll point it due south because I'm looking for culmination, solar noon. So suncalc.org gave me that information. That's about where I'll be, but I'll use the GPS and all that. I've shot other stuff from here before. I've shot moonrise from over here. I've shot the last lunar eclipse back in January from this spot, so you guys have seen this place already. I forgot to mention for county park, I did give magnetic declination. I printed this out on the 13th of September as well. We have 4.25 degrees. My Brunton set it for close enough. Like I said, my Brunton's only accurate about half a degree anyway, so I don't need to change it yet. And I'm coming up on the county park. Oh, it's called Countryside Park, but it is a county park. That's why I keep calling it that. I don't know what this clown's doing. Okay, we're at 12:33:24, and there's the setup. I'm going to confirm it. First of all, you can see, get real close. There's the park. That's west, east, obviously south. North would be that way. You can start to see the sun coming into view in the screen there. We still got minutes, lots of minutes left, but you can see it's pretty close to due south, and the predicted was 48, 49-ish degrees, and you can see right there it's pretty close. So what we should see is we should basically see the sun move. It's not going to move straight across, but it'll be near straight across. So I guess I'll start recording. Moving into frame. We are at 12:36:25. We're shooting for 12:41:08. (12:38:26). Sorry, it jumped a little, bumped it, sorry. We are at 12:39:46. Here's our time hack. So we're close. I bumped it a little, so we're off a degree. But actually I didn't bump it that much. It looks like it's coming almost due into frame as predicted, within margins of error. So, almost a solar noon. Maybe pan around. And we are 12:41:18. So we've passed it officially. Sorry. But I'll wait till it's closer to center of frame, and I'll give you a time hack again, and I'll stop this. Well, wasn't that far off. Not bad for eyeballing this whole setup. There's our present time hack. It says 12:43:05. Now, what you should start to see here in the video is, since we're past solar noon, I mean, sun is coming in from left to right, just as we predicted, but it should start to arc down slightly now that we're past the high point.
Video recording the sun, right?
Yep, exactly.
Using the Pringle can to block out the harmful rays.
But I got the filter on the Pringles can, yep. That's exactly what I'm doing.
Sorry, eclipse stuff. Correct?
Not eclipse stuff, equinox stuff. Equinox.
I'm not trying to be nosy.
Yeah, it's hard to see with the...
No, that looks cool. I like that. And it's a cheap camera lens.
That's the same filter stuff you use that's in the solar eclipse glasses. We ordered a sheet and just cut it on a Pringles can.
Do it. I mean, how much technically would that correct lens for your camera?
Way too much. It's a lot cheaper to do it this way.
That's a life hack. You know what? Right there. Dude, PVC pipe, you can make just a cheap one. But I guess with the actual lens, you could probably get a little more clarity. We should check that out, dude. It's pretty cool.
There's our Timac. Should be able to see it 12:45:54. Actually, the sun is a little bit above the red box, and it was a hair below before. I'm assuming this thing isn't moving, which with this big lens it is known to do. Should start coming back soon, but as soon as it's away from the red box, I'm going to stop the video. Only got 8 minutes of record time left. So, and here we are right now. Actually, what I'm going to try to do is see if there's any sunspots really quick. Yeah, I'm messing with it, but I get it right in the... There you go. That's what I was trying to get. I'm not seeing any sunspots. And then now I will call it quits. Now we are at 12:49:46. Okay, time to turn this off.